This is Sabr 3, a small air-breathing rotating detonation engine developed by our senior design team at the University of Central Florida. Our goal wasn't just to build another combustor, it was to bring together a full lab-scale propulsion system that combines shock-conditioned inlet flow with a hydrogen-air rotating detonation engine. In other words, we wanted to move one step closer to a more flight-relevant air-breathing detonation architecture.
A rotating detonation engine is different from conventional combustor because it uses a much more energetic mode of combustion. In most traditional propulsion systems, combustion happens through deflagration, where the flame propagates relatively slowly and the energy release is driven by heat transfer and diffusion. That process works, but it comes with a thermodynamic penalty because you lose stagnation pressure through combustion. An RDE instead uses detonation. A detonation is a supersonic combustion process where a shock wave is coupled with a flame front, producing a much more intense release of energy and a strong pressure rise. That is why RDEs are considered a form of pressure gain combustion. Inside the engine, that detonation is contained within a small annular gap where one or more detonation waves travel around the chamber at extremely high speed. Because those waves rotate at such a high frequency, the thrust output appears nearly constant. What makes this especially challenging is that the detonation has to remain self-sustaining inside a very confined geometry. So chamber shape, injector behavior, and operating conditions all matter a lot to whether this is going to work or not.
Sabr 3 is not a standalone project. It is the third phase of a continuing supersonic propulsion effort at UCF. Sabr 1 built the original foundation, the test stand, feed system, instrumentation, and the first annular air-breathing RDE. Sabr 2 advanced that effort by moving to a hollow combustor, improving the injector concept, and achieving hydrogen-air detonation with short successful runs. Sabr 3 built on both of those phases. Our contribution was to integrate that combustor heritage with a ramjet-emulated inlet path, so the combustor would no longer be studied in isolation. We were not only asking whether hydrogen-air detonation could happen, we were asking whether it could happen inside a more realistic inlet-coupled system.
Air from the feed system enters a converging-diverging nozzle, where it is accelerated to supersonic speed. That flow then enters a supersonic diffuser, where shocks compress the air, recover pressure, and reduce the Mach number before the combustion interface. This is where we will use Schlieren imaging to capture the shock waves and see how they react as the RDE starts up and runs. From there, the conditioned air passes through the transition hardware into the rotating detonation combustor, where hydrogen is injected. A pre-detonation device starts ignition, and rotating detonation is sustained in an annular chamber. Finally, the combustion products are exhausted downstream, so even though different subsystems were developed in parallel, Sabr 3 works primarily as a single integrated propulsion system, the airflow conditioning system. In order to simulate high-speed flight conditions, the converging-diverging nozzle was designed to accelerate compressed air to Mach 3. The nozzle contours were generated using a Python-based method of characteristics code. The diffuser was then designed to use oblique shock waves to raise static pressure, increase temperature, and bring the flow down to subsonic conditions appropriate for combustor entry. The supersonic section of the diffuser houses two acrylic windows where Schlieren imaging will be used to view the shock waves and how they are affected by combustor startup and running. Throughout the flow conditioning system, there are 3 pressure transducers and 1 thermocouple that will enable us to quantify stagnation conditions, target the pressure requirements of the combustor, and determine overall diffuser efficiency.
To validate the inlet concept, we used an extensive CFD campaign using SETI RAND's Reynolds Average Navier-Stokes simulations. Those simulations helped us understand the flow structure through the nozzle and diffuser, including the shock train, the terminal normal shock, and the sensitivity of the diffuser to downstream back pressure. The diffuser CFD showed a supersonic inlet, a subsonic outlet, and strong dependence on downstream conditions. Our target was to deliver air to the combustor at approximately Mach 0.2 to 0.3 after shock compression, with conditions suitable for hydrogen air mixing and detonation inside the annular chamber. Then, to validate the RDE injector scheme mixing in the annular chamber, a 3-dimensional, non-reacting, multi-species gas simulation with enhanced diffusion interactions was performed. This proved the effectiveness of the injector design given the inlet conditions provided by the diffuser.
The interface between the inlet hardware and the combustor is the most important design boundary in Sabr 3. If the diffuser delivers the wrong flow state, then the combustor sees the wrong Mach number, the wrong static pressure, the wrong mixing conditions, and potentially the wrong ignition environment. That means this interface is not just a flange or a connection point. It is a design contract between the upstream air path and the downstream combustor. This is also why Sabr 3 should be understood as one A-person team project. The success of the combustor depends on the inlet, and the success of the inlet depends on how the combustor responds under pressure oscillations and detonation-driven back pressure.
On the combustor side, Sabr 3 uses an annular hydrogen-air rotating detonation engine built on lessons learned from the past engine, but it's adapted for this new inlet-coupled architecture. The geometry had to satisfy several competing requirements at once: support rotating detonations, match our conditioned inlet flow, fit within manufacturing and test stand limits, and survive the expected thermal and pressure environment. Channel sizing and axial length were chosen using detonation, cell size-based heuristics, and previous engine data. An annular body was utilized because earlier phases showed us that this path in architecture was promising for hydrogen air detonation at the student scale we're working with, and offered novelty for the project given our injection scheme. Material selection also mattered. For our hot and highly loaded hardware, stainless steel was chosen because it offered a strong balance of cost, manufacturability, and structural performance for our repeated tests. Fuel delivery and ignition are central to whether an RDE works at all. In Sabr 3, hydrogen is supplied to the annular combustor through a plenum and triplet injector arrangement designed to remain strongly choked against expected chamber pressures. That matters because detonation creates rapid pressure oscillations, and without robust injector behavior, backflow and unstable mixing can quickly ruin the engine's ability to sustain a detonation. The injector concept we went with was chosen to improve upon earlier Sabr Engine 1 limitations by combining better mixing potential with a more practical geometry for this air-breathing configuration. Our approach to ignition centers on the use of a pre-detonator. Think of it as a torch igniter used in traditional rocket engines, but with some modifications to have it provide a seed detonation wave instead of a flame. Together, the plenum, injector, and ignition system had to solve the same core problem: deliver the right mixture at the right time in the right place, despite being inside of a very harsh and oscillatory combustion environment.
One of the most valuable parts of Sabr 3 was turning the design into real hardware. That meant machining parts, checking fit-up, refining mounts, adjusting hose and feed line routing, integrating diffuser and combustor hardware, and adapting the stand to support new geometry and measurement needs. As with most real propulsion projects, integration exposed practical issues that CAD alone can't solve: alignment, sealing, fastener access, hardware packaging, and the relationship between instrumentation and physical build. That process mattered because it transformed Sabr 3 from a concept into an experimental platform that future teams can continue to refine.
It's research infrastructure built to give future propulsion researchers a capable platform to build from. We inherited the stand, feed subsystems, and data acquisition architecture from prior Sabr teams and advanced them for this phase. This stand allows us to isolate subsystem behavior or characterize full system performance in a single campaign. Across all of them, LabVIEW-based control systems manage real-time pressure monitoring, remote valve actuation, scripted test sequencing, and high-rate data logging for post-run analysis. For a system involving high-pressure gas, hot exhaust, and controlled detonations, safety is a core engineering requirement, not an afterthought. We built formal procedures, defined operator roles, and integrated abort tech logic directly into control software. The goal is a system that future teams can inherit and operate with confidence.
We have successfully conducted multiple air cold flow runs with the fully integrated system up to 3 seconds, verifying that all airline valves and timing sequences are operating, and have been able to observe oblique shock trains throughout the diffuser throat without any specialized equipment. We've also successfully logged and processed pressure and temperature readings that validate the design Mach numbers being reached. Next steps are to verify ignition sequences, hydrogen line actuation, pressure and temperature readings, and hotfire the combustor with Schlieren and back-end high-speed imaging cameras to analyze the detonation waves, observe how the diffuser shock train reacts, and test our operational window and validate our performance envelope.
Sabr 3 established the first integrated ramjet inlet rotating detonation architecture on the Sabr program. We are Sabr 3, and this is one step forward in that larger mission.